All right, everyone. Another day, another Leetcode. It's your boy, the Canologist. All right, team. Let's begin. Number of 1 bits are a function that takes the binary representation of a positive integer, returns the number of set bits, also known as the Hamming weight. Set bits. It refers to a bit in a binary as a value of 1. Okay. Hamming weight. So Hamming weight, a string of numbers. Hamming weight of a string is the number of symbols that are different from the 0 symbol alphabet used. Hamming distance. String of bits. Okay. So set bits. Okay, so basically anything that's not a 0 is a set bit. Well, in binary it's just gonna be 0s and 1s. So let's start with deleting the comment here. Now what I want to do is look at some examples. So n equals 1 1. This is binary 3. Because 2 to the power 0 is 1, 2 to the power 1 is 2, 3. Output is 3. Explanation: the binary string has a total of 3 set bits. Okay. It returns the number of set bits. Oh, okay. N is an actual number, a decimal number. N is number 11. Right? So 3 output is 2 to the 4. So 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3 is 8. 2 to the power of 1 is 2, that's 10. And then 2 to the power of 0 is 1, that's 11. Right? So basically it's saying takes in the binary representation of a positive integer and returns number of set bits. Okay, so what I want to do is convert decimal to binary. So what I'm going to do is search up convert a decimal number to binary in Python. Is there like a quick function for this? Let me see this shit. Decimal to binary, recursive solution, convert a decimal to a binary number. Okay, so you actually have to do it. Okay. If the number is greater than 1, okay, so decimal was 34. So if number is greater than 1, convert to binary. What is convert to binary doing? Convert to binary n over 2. It's just calling on itself. Print percent to end. Oh, it's like printing the remainder of whatever Just gonna be zeros and ones because it's floored. Okay, so 34% 2 is 0. 34%, 17% 2 is 1. 16% 2 is 0. 8% 2 is 0. 4% 2 is 0. 2% 2 is 0. So where does it become 1? That's the thing I'm trying to figure out. 34% 2 is 0. The 17 is 1. 0, 0, 0. So 16, 8, 4, 2%, 2 is 0. So that's where I don't get why we have this. If the number is greater than 1. Because all I'd do in this case is I would just convert it to a string and then just count the ones. Python program. The binary representation. This actually makes the most sense to me. So you have to take a binary representation, which is an empty string, while n is greater than 0. I put 0 to 3 years. Professional background. IT professional. Oh, they just made a career roadmap for me. So this is basically it. This is what I want to try and emulate. Fucking hell, bro. Why do these guys keep shoving things down my throat? Rahul Jangu Tarun by top scalar instructors. Okay. Dude, everyone's got some intro to fucking thing course. I don't care, bro. You just have to actually build things and solve things. So right now I'm trying to take working solutions and make that work. So binary representation is the string. So let me call this bin rep for binary representation. If n is greater than or equal to 0 or is greater than 0, then we go binary or bin rep, because this is going to be our empty string that we're trying to formulate as a binary string. we take bin rep, and then we go Hamming weights. And then it's n%. Or no, it's n divided by 2. str n divided by 2. n% 2 plus this. So what I want to do is just add that and then call the function to run it again. Oh no, this is going to use bitwise. This is going to use bitwise, so it just shifts it by 2. So what do you do when you do bitwise is you just divide the number by 2 again. You divide the number by 2, divide the number by 2 until it's not greater than 0 anymore. Because when you shift a number to the left, when you turn something into binary, it's by powers of 2. So if you shift to the right by 1 bit, you're saying divide by 2. Because it's 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, right? So when you divide that, it shifts by 2 to the power of 1. So that's divided by 2. So you don't have to do any fancy things here. So all you have to do is this bin rep string. So what this is basically telling me is I'm going to go n % 2. So this takes the remainder value of this. So if I go 11% 2, the remainder value is going to be 1. If I go 10% 2, it's going to be 0 again. Let's shift to the right. So let's see. Let's just add it first. Plus. And the reason I don't plus equals it is because I have to add it to the end. No, I have to add it to the beginning. Right, so it's going to be 1, move to the right. Then I add another one, move to the right. Add another one, move to the right. Another one, move to the right. So I have this string. Then I want to call, do I call it within it? Yeah, I do. So n equals n shift right. And then I'm going to say return. So no, I'm not going to return bin rep. I have to return the output of bin rep. So now I'm going to go four bit in bin rep set bits then I just return set bits. So what I want to do is I want to check first for the bin rep. So binary representation is the final string. I'm trying to spit out a binary string of the original number. So if I have number 11, I want to go into this function. So and 11 is greater than 0. All right, so 11% 2, right, is going to be 1, because 11 divided by 2, if we go by the remainder and shit, it's going to be 5. It's going to be 5, remainder 1. So we take remainder 1, we add it to bin rep, right? So right now, this becomes a 1. Okay. Then I want to go, it calls the function on itself. No, it doesn't. So all it does again is n shift 1. You see what I'm saying? Return binary representation. Oh, okay. So this is a recursive function to spit out the string. It's going to keep repeating until oh, it's a while loop. Okay, so yeah, it's a while loop, not an if statement. That makes sense. This is why it keeps going. I was like, why the fuck does it stop? Because this doesn't perpetuate it. We're not using recursion. So this makes sense. Okay, so if we go here, we use the method that they're using. They're using a shift bit method. You could also do it using recursion and a floored 2 value to get the remainder, and then use the remainder. But both cases you have to use the remainder to formulate your binary string. Right, so let's start again. Let's just start again. Now that we've corrected the code. So we have 1 and 1, so 11. 11 divided by 2 is like 5.5. So that's basically 5, remainder 1. Right, so what I'm going to do is I'm going to take 1, this remainder, because it's str, and percent 2. So it takes the percent of 2, and then, so that's the remainder, turns it into a string and adds it. So this is going to be 1. Shift the bits to the right. Okay, so now it's going to be 5. So now it's going to be, and it's going to be 5, because I divided it by 2 already. Alright, so 5 is greater than 0. Okay, 5 divided by 2 is 2 with the remainder of 1 again. So it's going to be 1 plus 1. So I'm going to add it here. You see that? Then I'm going to shift the bits to the right again. So that divides it by 2 again. So if I shift the bits to the right, it's going to be, it's going to be 2. Right? So 2 is greater than 0. Right? So if 2 is greater than 0, and I percent it, so 2% 2, that's going to be 0. Because 2 divided by itself is 2 divided by 2 is 1. Anything divided by itself is 1, right? But the percent is 0. Right, so we add that to bin rep. Notice how we don't add it. We don't go plus equals, because then you would have gone 1 0, and this would have changed the answer completely. We have to add it to the front, to the left side. So we have to add it to the left side. So we're going 1 0. So 2 divided by 2 is 1. Remainder is 0. So we add the 0 here. Then we shift the bits to the right again. So now you have, what's it called? Shift the bits to the right again. So 2 divided by 2 is 0. In here, so 2% 2 is 0. So the remainder is 0. So 2 divided by 2 is 1. Remainder is 0. So now we go shift the bits to the right. So that's 2 divided by 2. That's going to be 1. 1 is greater than 0. So if 1 is greater than 0, that means 1 divided by 2, right, is going to be 0.5, right? So that's going to be 0, remainder 1. Because you can't divide, you can't technically divide. If you do the division on it, right, you're going to get a remainder of 1. So then you divide by 2 again. So you get that 0.5. But if you shift the bits to the right, the next element now becomes a 0. Right? So 0 is not greater than 0, so we don't continue. So that's essentially the same as rounding it down to 0. You see what I'm saying? So once you formulate the string 1011 that we get here, we go into our next loop. So if the bit in each. So if item in bit is a 1, add 1 to the set bits number. So it's going to be 1, 2, 3, 4. So if I go boom, bit thing, add 1. So now bits is 1, 0 doesn't do anything. 1 adds 1, so now it's 2. 1 adds 1, so now it's 3. Right? And then it comes out of that loop, and now we return output of 3. Okay, so this is the theory behind how I solved it. So I use a lookup because I want to figure out, how do I convert first my decimal number to a binary number, then how do I look at the binary number and take the set bits. As according to here, the Hamming weight is any set bit is a bit that's not 0. That's 1, 2, 3. And in a binary function, you're only going to have 0 and 1. So only 1s are set bits. So now that I counted all that, I should get an output of 3. I'm going to run it. What? What the fuck? 4-bit and thing, set bits. Okay, so let me try this. Maybe it's because I'm using a output 6 expected 3. Output 6 expected 3. Oh, you know why? Do you want to know why? It's because I fucking forgot to delete this at the end of the example. I'm like, wait, what the hell is going on? Like, everything is exactly the way I planned it. There you go. See? So you get output 3. Sorry guys, while I was explaining to you, I forgot to clear this out, and then it ended up doubling the output. So now I have 3 here, and then if I go to case 2, which is 128, now you just extrapolate the logic, right? So once you can solve it for like the smaller functions, like we only had like a 4-bit thing. Now if you have like fucking 8 bits, or if you have like 30 bits or some shit like that, or fucking whatever, it still works because it's going to be an O of n solution. It only goes up with the number of bits, right? So it's using a for loop and it has to go once through each thing, using a while loop, which is going once through each thing. So it's going to be O of 2 of n, 2 times n, and then that reduces to O of n, right? And then in terms of space complexity, you have a O of n space because it scales with the number of bits. So as the number of bits increases, the number of string elements increases by n, right? So you have O of n space. So then you have O of 1 space for this. So it'd be O of 1 plus O of n. Extrapolate, it's going to be O of n space, O of n time. So now we're going to look at submitting it. And there you have it. Right? So my O of n time and space speed is 90% of the other solutions. And it's easy to understand. As I traced with you, once you go through it a few times, you can get how this works. I recommend watching a video on this bitwise operator just so you understand how it works. Here, I could even show it to you on the whiteboard. We'll do a quick whiteboard recap of the bitwise just so you guys can get the value you need. So let's say it's 1, 0, 1, 1, right? If I shift to the right, so anytime you use, okay, wait, I don't like the way this fucking marker is doing shit. I need a bigger point on my marker. What the fuck? Oh, I'm like, yo, dude, why can't I use it? Okay, so now that I have this, I can go 1, 0, 1, 1, just like the example here. I don't need this anymore. So if we go back to the original example that we tested on, it was this 11. So this is equal to 11 in decimal, and then this is the binary representation, right? So if I do a shift bit to the right, whatever direction you shift to, you add a 0 on the end. So for example, 1011, if I right shift n by 1 bit, that's saying shift 1011 by 1 bit, right? Essentially what I'm doing is I'm creating this. I'm shifting the right, so this bit over here gets shifted, so it gets cut off, and I add a 0 in its place at the end. So now I get 0, 1, 0, 1. This is what happens after a right shift. And for example, if we were to do a left shift, just for example's sake, it would be n left shift 1 bit. So you know how this would be 11? Whenever you right shift, you divide by 2. Whenever you left shift, you times by 2. So now let's check what's going on. So now we're going 1. I'm going to shift left to by 1 bit. So it's going to be 1011. Right? So now we do the opposite. We add a 0 to the end of whatever. Right? So now this is going to be equal to 1, 0, 1, 1, 0, because now we times it by 2, right? That's the answer here. So let's take a look at what happened. This is binary 11 in decimal right here. Let's see what happens when we shift it to the right. So let's convert this. 2 to the power 0 is 1 plus 2 to the power of the 2 to the power of 1 is 0. We don't have anything. 2 to the power of 2 is 2 to the power of 0. 2 to the power of 1. 2 to the power of 2 is 4. 5. You see that? So it's basically 11 divided by 2, remainder 1. Right? So it only does like whole number division. So you cut off the decimal. It would have been 5.5, right? But now you get 5. So it's basically n floor 2 is what happens when you shift by 1 bit. Right? Now let's see the opposite effect. Right? We shifted to the left. Right? So it's going to be 2 to the power of 0 is going to be 0. 2 to the power of 1 is 2 plus 2 to the power of 2 is 4 plus 2 to the power of 3 is 8, that's 0, so nothing. 2 to the power of 4 is 16. 22. So as you can see, so this is R, L. If you shift to the left, so this is R, shifting to the right. If you shift to the left, so N left, 1, it's n times 2. See? So you get 11 times 2, or you get 11 divided by 2 floored, which is 5. So if we go back to the function here, we're shifting to the right, right? So with every iteration of 11, we go 1, shift to the right, times divided by 2 again, shift to the right, times it by 2 again, shift to the right, right? But in this case of the string, we're adding it to the left, to the most significant bit, right? So at the end, you get this string formulated, 1, 0, 1, 1. But we're adding it as 1, because we're dividing, we're getting a remainder, adding as 1, dividing, getting a remainder, 0, dividing, getting a remainder, 1. We can't divide anymore, so we add it to the string and that's it. Then we go count each bit and we get the set bits from the count, so because we only get 1, 2, 3 from this count. So as you can see, we passed the solution, and I explained it all to you on the whiteboard with the left and right bitwise shift operators. So if you like this video, please give it a thumbs up, subscribe to the channel, leave your comments below. Eager to hear from you guys. Also getting a lot more engagement, so I'm really glad you guys are getting the value you need out of this channel. So with that, Knologist out.